Hi everybody, my name is Mr. Boney. I'm one of the UMTYMP algebra instructors, and this week I'm going to make some videos helping you out with 2.1 through 2.4, but I just wanted you to see me and say hello before we dive in. So we're going to be seeing a lot of things that look like this, and just a little quick review of some of the terminology that we're going to use a lot. We're going to be saying things like left-hand side and right-hand side a lot. So in terms of, or in reference to the equal sign, the left-hand side is here, right? And the right-hand side is here. So it's exactly what we mean, sort of to the left and to the right of the equals. And overall, what we call the entire thing, the whole thing, is an equation if it has an equal sign in it. Okay? That's pretty important because there are things that we're going to deal with that aren't equations. They don't have equal signs in them. We call those expressions. We don't want to overuse the word equation. And then as we're going through today, keep order of operations in mind because we're going to be manipulating these things with order of operations very much on the forefront. We're going to be doing a lot of undoing of things, so we might need to think about that in reverse. Even though this may be review for a lot of you, we do want to formally say then that an equation is two expressions, right? Two expressions separated by an equal sign. So it has to have an equal sign in it. We're going to be dealing with first degree equations to get started. And first degree equations are equations, but that have one variable and an exponent of 1. One thing that's worth clarifying here is when we say one variable, we mean one variable like either all x's or all y's or all b's or all c's, but not a mix of them. So if an equation has x's and y's in it, it's right away not a first degree equation. Okay? And then a value that we're looking for many times is a solution. And a solution to an equation is a value that makes it a true numerical statement. So if we had 2x plus 1 equals 17, then 8 is a solution because when we substitute that in for the variable, this is a true mathematical statement because 16 plus 1 would in fact equal 17. 16 plus 1, 17 equals 17. So this is the example that I would like us to work on in practicing solving equations. So when somebody says to solve an equation, our goal is to find a solution, right? So solve is the verb to find the solution. So we're looking for a number that we could substitute in this x position and make this overall expression or make this a true mathematical statement. Some number over here equal to some number over here that are in fact equal to each other. And that's what checking our work is going to look like. Not just doing the problem again, but making sure that it does in fact make the equation true. We're going to use these properties to help us solve these equations. Okay, we have the addition property of equality, and we have the multiplication property of equality. Add these to the list of your property names that you need to know. But overall, what it's saying here is if two things are equal, then no matter what, if and only if, and little side note, IFF is not a typo. That's shorthand for if and only if. You're going to see that a lot in math and logic. But if and only if A equals B, then A plus C is going to equal B plus C. And if we decipher this, what essentially it's saying is we can add the same amount to both sides and it will still be equal. Keep in mind also that we're dealing with all real numbers here, so C could be negative. So essentially, even though this is saying the addition property of equality, we know subtraction is just adding a negative, so this works for adding or taking away from both sides. Similarly, multiplication property of equality holds. A equals B if and only if C equals BC, so that means we can multiply both sides by the same number and we get a true equation still. It still holds, okay? This if and only if, the power of it is that it works both ways, meaning if you have the A plus C equals B plus C, that you can go backwards and conclude that A equals B. essentially meaning you could take away the c's. If they're there, you can strip them away, and if you strip away the same thing on both sides, it's still equal. So that's another sort of way you can reason out that it works for subtraction. And down here, that if you make the c's go away, essentially you're taking out a factor, you're dividing. So addition, subtraction, multiplication, division, long story short, if you do the same thing to both sides, the equation is still true. Before we do an example, then let's summarize our overall strategy for solving a linear equation. And before we even do that, let me just take the opportunity to say linear is another way that we refer to first degree equations. So what are we going to do? We're going to simplify both sides. That is, maybe combine like terms, maybe get rid of parentheses, just overall manipulate. Then we're going to use the addition property of equality to isolate the variable terms on one side and the constants on the other. So we're going to sort of reorganize so we can group all the things together. Then we're going to use the multiplication property of equality to make any coefficients of our variable go away so that we have just one of them, right? We want it to say essentially 1x equals, not 5x equals. And then we're going to check our solution, which again doesn't just mean do the problem again, but really analyze what does a solution mean? What is a solution supposed to do? It's supposed to make the equation true. All right, let's use these steps to solve an equation. So first off, solve is just a verb that means find the solution. So those words are linked. Step number one is simplify. So in this case, we could simplify by getting rid of the parentheses using the distributive property. And we're doing this sort of independently on the left side and the right side, simplifying within those sides. If you've ever seen somebody draw the line here, sort of make these train tracks of equal signs, it is to help sort of visually see that we can only manipulate the left-hand side and the right-hand side, but they can't mix, right? Like I can't combine this 10x and this 12x to make 22x because they're on opposite sides of the equal sign. Okay, so what do? We use our properties of equality. So our addition property of equality says we can add and subtract anything we want as long as we do it on both sides. So if I wanted to isolate these x's, I could make the choice of subtracting 12x from both sides. I would want to do that because 12x and negative 12x together adds up to 0, and so that means I don't have to write it anymore. 0 minus 28 would just be negative 28, so it's essentially this is canceling out. You see a lot of people or hear a lot of people say canceling out. And many times that just means that either adds up to 0 or divides out to be 1 and gives us those identities that we don't need to write as much. Okay? Showing our work is really, really, really important here. We want to make sure that we understand that at this phase in algebra, even if this is review for you, what we're intending to do here is demonstrate we know how to solve. So if you are skipping that work, you're not essentially accomplishing the point of the problem. And keep that in mind when you're trying to decide what work needs to be shown. That's an issue in early UMTYMP for a lot of students is how much work should I show? Try and keep in mind my sort of golden rule is, or my rule of thumb is, well, let's demonstrate the point of the problem. And the point of the problem here is demonstrating that we know how to solve. So I'm going to show every step. In a couple months, right, down the road when we're on later problems, if the point is not just the act of solving an equation, but getting a solution to a system or something like that, I can maybe take more liberties to skip some steps if that's not the point of the problem. But here it absolutely is. So we want to make sure that we show all of these steps, even if you can do them in your head. All right, now we've got negative 2x on the left-hand side, minus 33 on the right-hand side. We need to get rid of this negative 2. Be careful, early equation solvers sometimes look at that minus 2 and think, okay, the opposite of minus is plus, but keep in mind that's just a negative 2 multiplying x. So we are going to want to use the multiplication property of equality to divide both sides by negative 2, and that is going to give us a 1. Now you hear again a lot of people say that these cancel out. The reason that cancels out is because if that does reduce to 1, and we know 1 times anything is itself because that's the multiplicative identity, then we have just x equals 33 over 2 here. Okay? So what would checking our work look like here? Well, checking our work again isn't just doing the problem over again. Checking our work here is substituting this into the equation and making sure it is in fact true. So if we take this 33 over 2 and we substitute it into the equation, hopefully the result here is that both of these sides are equal. So let's go ahead and do that work. So order of operations, multiplying here is going to give us 33 because times 2 and divided by 2 are just going to undo each other, right? Over here, it's going to take us a little bit more effort. This is going to be 99 over 2 because, right, 3 over 1 times 33 over 2 is going to be 99 over 2. Minus 7, I'm going to have to go ahead and get common denominators there to put those together. Again, we're just manipulating on both sides until we hope these are the same. All right, we're going to have, what, 99 minus 14, that's 85 over 2. All right, and then let's see if we can do this. 5 times 34, that's 150 and 20, so that is 170. And then I would personally think about this 4 divided by 2 as being 2. So this would reduce to being 2 times 85, which is 170. Hooray, it worked out, so we know that our solution here, even though it's a fraction, is correct. For these last couple problems, I just want to really stress in UMTYMP that it's not all about getting the answer to the problem. You might look at this and know the answer to the problem after a little bit of thought, and you guys might even have some really creative ways to think about it and do it in your head. But this is an algebra course, and the intention isn't just to get the answer, but to demonstrate that you can use algebra to get that answer. On a quiz or a test, very little, if not no credit will be awarded to just an answer to this problem, even if it's correct. You need to have an equation and a solution to that equation that provides that answer. So then the question becomes, how are we going to illustrate or demonstrate those 3 consecutive integers in a problem whose sum is 42 in an equation? Especially if we're dealing with first-degree equations in which we only want one variable. How am I going to have 3 separate numbers represented by one variable? Well, the key is this idea of consecutive. Consecutive means sort of in a row, right, or next to each other. And if we're dealing with integers, those would be numbers like 1, 2, 3, or 3, 4, 5. So if we want to represent this with a variable, we could go ahead and say one of the variables is x, and we could say, and we want to communicate to somebody that this might be the first integer in this row. Then we want to demonstrate the next integer in that row without coming up with a new variable. We don't want more variables than just an x, otherwise we're not going to be able to solve. So we just have to think through, well, again, what does consecutive mean? It's the next one, so one more than it. So that's the next one, okay? And then the next one after that would be the last one, all right? Finally, we know that these then 3 add up to 42. So we have x plus 1 plus x plus 2 equals 42. And you might see people write parentheses around these just as a visual of saying, all right, these are the 3 integers we were talking about. They don't really do anything in this case, though, so feel free to not write them. But if you see them in a text, that's what's going on. So step 1, simplify. Since we're on the left-hand side of the equal sign, we can combine our like terms here. We would have 3x plus 3 equals 42. Then we can use the addition property of equality to take away 3 from both sides here, and that leaves us with a 3x equals 39. Then we can divide by 3, and we get x equals 13. You might be tempted to stop here. I see a lot of students when they get something equals, they're like, yay, I'm done with the problem. But make sure that you answer the question. And the answer here, or the question here, was saying find 3 consecutive even integers. So until you find 3 integers, you haven't answered the question. But this is where, especially writing something like this down, will remind you, oh yeah, we had the first integer is 13, but the next 2 are important as well. So the answer to this question then is 13, 14, and 15 are 3 consecutive integers whose sum is 42. Yay! So we're done. Little recap of what we did there. Most importantly in word problems for students in UMTYMP, make sure to define your variables. Write what your variable means. Literally write it out. In our last problem, we said that x was our first number. That's really important. If you just go ahead and write an equation, even if it's correct, people might not know what your variable represents, so you must write it down. Once you have an equation that describes your situation, you can solve that equation. And when you're solving, make sure you're showing your work and you're showing all equivalent equations that you work through vertically, right? Sort of step by step by step. And then when you get done solving, make sure you actually answer the problem. Like in the last one, 13 wasn't the answer to the problem because the question was to find 3 integers. Again, one more time, I can't stress it enough. This is an algebra course. You do need an algebraic solution. It's not just what is the answer to this question, but can you write an equation and show algebraic thinking to get the solution? You have to use an equation. For our last example, I chose one that students are often tempted to make several variables for. And even though there are skills that let us do that, called systems of equations, keep in mind that we're not there yet. And so if you see a problem in this section, the intention is that you use one variable. We're dealing with first degree equations here. So if we read, suppose that Maria has 150 coins consisting of pennies, nickels, and dimes. We just want one variable. So what should it be? Should it be the pennies, the nickels, the dimes? And if we go ahead and read, the number of nickels she has is 10 less than twice the number of pennies. That might be an early clue that if we define our variable as pennies, then we can write the number of nickels as an expression involving that. Then the number of dimes is 10 more than 3 times the number of nickels, which might scare us a little bit, but if we get started, I think you'll see what we can do. So let's make our variable p, and we want to let everybody know what that represents. So that is the number of pennies. Okay, and then instead of saying n is the number of nickels, we want to write the number of nickels in terms of the variable we just defined. So it's 10 less than twice the number of pennies. So 10 less than is 10 taken away from twice the number of pennies, which would be 2p. So 2p minus 10 is the number of nickels. All right, so, oops, I spelled nickels wrong. Nickels, okay. And then the number of dimes is 10 more than, so adding 10 to 3 times the number of nickels. Well, this is our number of nickels. So we can take that and we can write 3 times that plus 10. We would just take advantage of our ability to use parentheses. So that expression then would be the number of dimes, okay? And then overall, these are quantities of each of them. Again, this isn't value, this is a number of coins in this problem, but other problems might have value, and you can use multiplication to do that. But this one, we're gonna say all of these things together then. All of these things together total up to 150 different coins. And now we can use our equation solving skills. So we can combine like terms, we can get rid of parentheses, we can do all of that fun stuff. So I use the distributive property there. Now I can collect like terms. We've got what, 1, 2, 3, 4, okay, we've got 9p. We add 10 and negative 10 together, and these two, right, a total to 0, so that means we just have minus 30. And now we can use our addition property of equality. I ran out of space here, but you guys can keep going on paper. Again, trying to do this vertically. I'm not modeling that very well in this problem, sorry. And we get p equals 20. So make sure then that you answer the question, because the question was how many coins of each kind she has. Just saying 20 pennies is not enough. Let's answer the question. She has 20 pennies. And then, oh, the number of nickels is 2 times that minus 10. So that would be 2 times 20, which is 40, minus 10 is 30. And then 20, or 30 times 3 is 90, plus 10 is 100. So we could use that description, but we could have also used the idea that there's 150. So once we know that there's 20 pennies and 30 nickels, I did that wrong. Let me back up. I was writing pennies the whole time. That's no good. I was worried about the number and not writing down what it was. All right, we've got that. Hooray! Make sure to answer the question.